This lecture is on the applications of polynomials. So I went and found a problem at the Physics Hyper textbook, which you can find at physics.info. And they recorded some data for a falling object. If you look down here in the time column, you have 60ths of a second. So this is 0 seconds, 1/60th of a second, 2/60ths of a second, 3/60ths of a second, and so on. In this column, we have the distances the object has fallen from the point from which it was dropped. So if you can imagine, so here's some object, it's dropped at t equals 0. You start your stopwatch. At t equals 1/60th of a second, it's fallen some distance. And what is that distance according to our chart? 0.03. Clean that up. Or 0.003. After 2/60ths of a second, the object has fallen further, and this distance is, well, it'll be the new number 0.008 minus the previous distance 0.003. So this distance from here to here is 0.005. Notice the gap increased, and as time progresses even further, we go another 60th of a second into the future. And, well, the next increment is 0.015 minus the previous 0.08 would be 0.007. So from here to here is 0.007. So it should be clear that the object is falling further distances as equal amounts of time pass. So, well, if we take that information and plot it, if we plot time on the t-axis and distance, we'll call that x, on the vertical axis, then these ordered pairs, these red x's down here, are the ordered pairs from here. So this is 0, 0 right here. And then after 5/60ths of a second, 0.037. So that's the 0, 1, 2, 3, 4, 5. So right here, that would be 5/60ths of a second, because each of these numbers here in the time column get multiplied by the 1/60th factor up here. So 5 times 1/60th, 5/60ths, corresponds to 0.037. And right here, 15. And 0.283, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This point here is 15/60ths of a second, and the object was then 0.283 meters from where it was initially dropped. And then 15 16, 17, 18, 19. So 19 and 60ths and 0.433 would be this point here. All right. Well, when you take all of those points and you plug them into the program that I coded up that you can find here, it will tell you the quadratic function that best fits this data, and that's this blue line. So the blue line is x of t equal to. So the a is the coefficient of the squared term. Our variable is t, our dependent variable. So we have 3.96. We'll use 2 digits. 96. Well, let's use 3 actually. So 964 t squared from here and from here. And let me make that clear that this is a 4. Then we have 0.140 and round that 5 rounds that 0 to 1. So plus 0.141 t. All right, so that term is good. And then c minus 0.01, and the 5 will round that to 2. 0.002. So that is the quadratic that best fits the data, which I'll write in red. That's these individual points. All right. There's a finite amount of points. The quadratic gives us a way of getting a function that will tell us the position at any time. All right. Or the best estimate we can come up with, at least. So let's take this quadratic function here and we'll use it. Down here. Because the problem says use the polynomial calculated by the program and the graph to estimate the position of the objects when time is 5/12 of a second. So that's t equals about 0.42 seconds. Okay, so estimating, here's the graph. T equals 0.42 seconds, or 5/12 of a second, is right about here. T equals 0.42. Or 5/12, about 0.42. Well, if we go straight up from that point, we get to here on the graph. And if we project back, let's see if we can get a line tool here. or somewhere about there. So maybe somewhere right about here. That looks like 0.7, a little bit more than 0.7, because right here would be 0.7, halfway between 0.6 and 0.8, so a little bit more than 0.7. I'm going to estimate 0.73. No, 2, because the line looks a little slanted up. So the guess by inspection is 5/12 and 0.72. Now to get the approximation, take our polynomial and we're interested in t equal to 5/12. So x of 5/12 is 3.96 5/12 squared plus 0.141 times 5/12 minus 0.002. And let's plug that into our calculator. So we have 3.96. Well, first we're plugging 5/12 in. So we do 5 divided by 12. The number we're evaluating, store that as a variable with the variable key, x. Now type your polynomial. So we've got 3.96 times, well, the variable squared, 3.96, and then x squared plus, oops, plus 0.141 times 5/12. Oops. So plus 0.141 x, then minus 0.002, 0.002, and then enter. So 0.74425, and that's not bad. Zero 0.744 right there. All right. So the prediction by the quadratic of best fit is that the object will have moved 0.744 meters, 5/12 of a second. after the object was released. Released, not released. Let's see how that worked out. Well, here's the actual data point right here. So at 0.42, about at 5/12, we have 0.749 meters. That is the error is equal to the absolute value of actual minus prediction. Actual minus predicted. So our error is the absolute value of 0.749 minus 0.744, which is 0.005, or it's accurate up to 5/1000ths of a meter, 5 millimeters. And formally, prediction off by 5 millimeters. That's not too bad. That's pretty good. All right. So that's how a lot of science is done. Scientists go out and collect finite bits of data, and then mathematicians and computer scientists figure out ways to fit functions and curves to that data so that you can draw conclusions and make predictions and do some science and engineering. All right.